Yeah, so welcome back, everybody. Had a nice lunch break, and now we're going to get started with our afternoon session. Our first talk is given by Ezad Shojaee. He works as a postdoc at NIST Boulder, and he works with Manny Knill and Scott Glancy, who were my postdoctoral advisees. So he's kind of doing what I was doing a few years ago, doing it now. And so I'm excited to hear about what my former group has been working on. And he's going to give us a talk on the tomography of entangled macroscopic mechanical objects. So thanks, Ezad, and you can take it away.
Well, thank you. Good afternoon. As Peter said, I'm Ezad Shojaee. I'm a postdoctoral researcher at NIST Boulder, working with Scott and Manny. First, let me thank the organizers of Quilt for inviting me to give this talk here. I'm gonna tell you about our work on tomography of entangled macroscopic mechanical objects. This was an experiment which was led by Shlomi Kotler, a researcher at NIST at the time, who is now a PI at Hebrew University of Jerusalem. And in addition, I would like to go over what I've been doing more recently regarding the quantum networking project, which is a study that I've been conducting alongside Aiko, Kyle, Curtis Rao, Alex Kwiatkowski. And the theory PIs of both these projects are Scott Glancy and Manny Knill. So why are we doing this? What is the motivation? The ability to demonstrate quantum entanglement in macroscopic scale would be the triumph on its own, I would say. Quantum entanglement is the most interesting feature of quantum mechanics, and to demonstrate it in a lab, I would say, is fundamental. Here I've put a splendid work out of Anton Zeilinger's group back in 2014, I think, which in my opinion is an indirect demonstration of entanglement among photons. I would definitely encourage you to read this paper, but the point is that the photons that are captured in the photodetectors have not passed through the objects, but the fact that they are entangled with the photons that they do makes them able to capture an image of whatever they put in here as the object. Entanglement has been directly measured before in atomic ions, but to directly measure it in macroscopic objects would be a challenge. People have started to do things regarding that. You can see some probabilistic schemes in the literature or some indirect inference to witness that entanglement in macroscopic objects. But it has not been done directly before. So this is what we accomplished in this work. So basically we want to entangle two drumheads, not of regular size, but of the size of a tiny hair, I would say, of orders of tens of picograms. And not only we like to see the entanglement, but also we want to use this entanglement to go beyond classical physics. We need to entangle, and to do so, we need to entangle the nodes of the so-called quantum network. Let's say you have two quantum machines, Q1 and Q2, like what they have in IBM, Google, or many other companies nowadays, and you want to entangle them. Even if they are in the same lab, on the same tabletop, you need to work hard to establish quantum entanglement between them. And this is basically what I'm gonna talk about in the first half of my talk. Then you want to extend the range of your network and connect them when they are farther, when they are different labs, kilometers away. And what do we need to establish such a fragile correlation between these two quantum machines? Is going to be the subject of the second part of my talk. So this would be the overview of my talk. I would first talk about entangling two macroscopic mechanical objects, which would be the first time that it's been done in the literature on macroscopic level, and directly I would talk about these terms later more. And in the second half, I would lay the grounds on sharing entanglement at far distances and tell you about what is our proposal to do so. So here it comes, the first part of the talk. On the left here, these are the, by the way, pictures cropped from the arXiv version of our paper here. On the left, you see SEM of a device like the one used in the paper. You have two aluminum drums which are suspended above a sapphire substrate, and they are basically two harmonic oscillators which move perpendicular to the substrate with frequencies of order tens of megahertz. And each of these drumheads are the top part or top plate of a capacitor, as you see on the right in the schematics of the experiment, where the bottom plate is fixed to the substrate. And on the circuit schematics on the right, you would see that the mechanical motion of these capacitors, or the top plate of these capacitors, modulates the frequency of the microwave cavities. So if you use an incoming microwave field, it would be Doppler shifted, and that is what you capture to gain information about the position of these oscillators. And you use circulators here to separate incoming from the outgoing field. This would be the diagram of the experiment from a theorist's point of view. You have basically three harmonic oscillators. One in the middle is the microwave cavity with A hat as its field operator, and then you have B1 and B2, the mechanical drumheads operators, and G sub B and G sub R are the coupling rates. To understand what's happening with this interacting Hamiltonian, let's for a moment assume that the system is closed, meaning that whatever you have in the system is this interaction Hamiltonian. And what is happening is that because of this two-mode squeezing operation, A and B1 become entangled. And then because of this beam splitter type interaction, whatever you have in A gets swapped to B2. So that's how you can think of entangling B1 and B2 in this experiment. And how you fix the amounts of GB and GR by the pulses that you use in the experiment, actually. But as I said, these three oscillators are not isolated from the world outside. You have fields outside which are interacting with this system, as well as our input field and output field, as well as our input field. We are probing the system at the end of the day by shining a laser and capturing whatever reflects of it. That is basically what qualitatively happens when a police car pulls you over because of speeding. So to formulate how this system of three oscillators interact with the fields outside the cavity, we use the input-output formalism, which I do not have to go over that, but if you are interested, you can learn about this in these two brilliant references, I would say. So back to our experiment, the Hamiltonian in the rotating frame with respect to three terms of Hamiltonian, as we saw before, reads something like this. And the magnitudes of GB and GR, as I said, are controlled by microwave pump pulses. And whenever you include the effects of the environment interacting with your system, you will end up having these Heisenberg-Langevin equations of motions. So again, just to make sense of it, let's for a moment assume you do not have any interaction with the medium or environment. This would be the Heisenberg equations of motions for A, B1, and B2, the fields of interest. But then the fact that the system is open, you are interacting with the environment, Under certain assumptions, which are definitely met in our experiment, you can slightly modify this set of equations and end up with Heisenberg-Langevin equations of motion. You will see damping here and a fluctuating noise term, which comes from the fluctuations of the input field. There is some cool relations between this set of equations and the fluctuation dissipation theorem. So I told you that we shine a laser on our system, we capture the field that comes out. But there is another complication in our experiment, and that's the fact that, that's the following. The signal we capture suffers from both loss and added noise. The loss would be the portion of the signal that goes into the environment and basically is lost to the environment. And the added is the vacuum fluctuation, which does matter in quantum realm. So how do we model that? We imagine an imaginary beam splitter with transmissivity equal to the transmissivity of the medium, the lossy medium. So the unused, let's say alpha is your signal. Beta is the unused port, which gets injected by vacuum. That's how vacuum fluctuations come about around your signal. And then this port that you do not measure, the blue one, is whatever information that's lost to the medium. And by going through simple math, you can show that the quadratures of your signal, x and p for each one of the drumheads, which here, let's say alpha is alpha captures x and p for the first drumhead. You can show that by this beam splitter model, they evolve as following, where these C operators are zero mean and variance half. They are basically Gaussian random variables. And let's call this, whatever happens to alpha here, MATCAL F. So the way that we model the loss and added noise in our experiment is following. Each of those signals, one for the first drumhead and the second for the second drumhead, they go through this MATCAL F map, which takes care of both added noise and portion that lost to the information. And if we could manage to show entanglement between these two weakened and noise added signals, first of all, it would be an achievement on its own. And second, it also suggests stronger entanglement at the source. And before going to the results, let me tell you how do we actually witness this entanglement among these modes. Remember the Perez-Hordicki criteria for witnessing entanglement was that if you do partial transposition on a quantum state, and if you end up with a state that is legitimate quantum state, which is positive, so if the partial transposed of your state becomes positive, then the initial state was separable. So if you do the partial transposition and you end up with something non-positive, it is a witness that your state, was not separable, so it was entangled. And in the case of Gaussian CV quantum system, Gaussian continuous variable quantum systems, which basically are the states that can be parametrized or characterized by their first and second order moments and live in infinite dimensional Hilbert space. These two brilliant papers in 2000s actually show that this condition is equivalent to the following criteria. If you form the covariance matrix of two continuous variable systems of your own, then, which turns out to be of this form, which I don't care at the moment, then one can show that if you calculate the symplectic eigenvalues of this matrix, there's a theorem that ensures you that you would have symplectic eigenvalues for this matrix. If you evaluate the symplectic eigenvalues of the partial transpose of this covariance matrix, then the minimum being smaller than a half is your witness. So just what you need to do is to form the covariance matrix of your two-mode CV system, evaluate this algebraic relation, and if your minimum simplicity eigenvalue is less than a half, you have entanglement. And just a couple of words about partial transposition. We know that it is equivalent to reversing the momentum of the second mode. And if you look at the papers that I mentioned here, you would see that this map is kind of reminds, at least me, of flat space metric, all ones and 1 minus 1. But we don't care at the moment. But that is our metric, which I would refer to as Simon and Duan criteria later.
Sorry, I just have a brief comment. This is Mark. Can you go back to the previous slide? I think your first line, it should be flipped. You know, if rho is separable, then the partial transpose is positive, right? And then that's equivalent to the contrapose.
Oh, yes. Oh, it is.
You hesitated a bit when you got to that part, and so maybe pay attention more.
Yeah, I think that's, I noticed there's something wrong there.
Okay. All right. Sorry, go ahead.
No, thank you for correcting that. Well, sorry about the messages that I get here. Well, this is how we try to estimate the entanglement at the source. First, we construct what I would call the sample covariance matrix from the data we get in our experiment. And just by the way, the data is the heterodyne signals, which capture both X and P of the quadratures, X and P quadratures of each drumhead. Then we look for positive matrices, which when you act the map on them, minimizes the distance between what you get and what you measured in your experiment. So look for basically minimize over positive matrices, which are not only positive themselves, covariance matrix has to be positive, but also they are Heisenberg friendly. This is the manifestation of Heisenberg uncertainty is that your covariance matrix has not only to be positive, but has to satisfy this form, which J here is symplectic form, and the fact that you have two modes, omega here is tensor sum of those. So going to the experiment finally, this is a movie of the data captured from the mechanical drumheads. Here you see XMP of the first drumhead, XMP of the second drumhead, and sorry. Then you would see that as time goes by, you are building up positive correlations between the positions of the mechanical oscillators and negative correlations between the momentums of the oscillators, which reminds everyone of the EPR state. And finally, looking at the data points, on the left panel, you would see the entanglement in the measured, basically the entanglement in the measured signals, so after all the loss. And on the right, you would see entanglement at the source. Here in these two plots, the points are the experimental data, which they include tiny confidence intervals on top of them. The fact that you cannot see confidence intervals is a manifestation of having good statistics in this experiment. And how did we get these confidence intervals? By experimental bootstrapping. And how does experimental bootstrapping go? You resample many times from your experimental data, and then you sort them out, sort the criteria that you want to get the confidence interval for from low to high, and then throw out the percentiles, 0.1 percentile and 99% percentile, and you would get your confidence interval. So here it is actually. You are looking at entanglement, directly measuring the experiment. And as I said here, at least on the left panel, even after the loss, you are looking at two mechanical drumheads of size of a tiny hair entangled. Remember, whenever your new here is that minimum symplectic eigenvalue that I mentioned before, and wherever that's below half, That's a witness of entanglement between the two drumheads. So two tiny objects, but not microscopic, macroscopic, are entangled here definitely. This black thin line is the theory, which was developed for this experiment in the paper. And this shaded area is the uncertainty and the theory you get because of the systematic error. Because in this experiment, not only you have systematic error, but you have systematic error as well. We have information about the loss to the medium, but not exactly. So that includes some systematic uncertainty in our experiment. So that is the shaded area about. And what are these insets about? These are for the last point in both plots, here and there. And this is basically the 1 sigma of the systematic error on top of the measured data. And I told you about how do we witness entanglement at the source. This is what we did in the right panel. And you would see that the amount of entanglement characterized by how much lower than a half is your minimum symplectic eigenvalue. You get stronger entanglement before the loss, which makes sense. So I think I need to emphasize that the entanglement that was demonstrated in this work not only was the strongest so far, but was among the most massive objects. And as I told you in the introduction, people have tried to witness entanglement among macroscopic objects before, but they were either probabilistic or they tried some indirect inference to witness entanglement. But here it's direct in the sense that we are doing full tomography of the states. See, we start with Gaussian states. The dynamics is Gaussian preserving, so your state is Gaussian. If you form the covariance matrix, basically you know everything. And that's what we did in this work. Full tomography, and that's the witness of entanglement. So hopefully I'm doing, how I'm doing on time. Hopefully I have some time to go over the second half of my talk really fast, which is about sharing long distance sharing long distance entanglement. So the first part of the talk, I would say, was about the ability to entangle two objects on the same tabletop. But what if you want to extend the range of your quantum network? Let's say, again, you have two quantum machines, Q1 and Q2. If they are on the same fridge, in the same tabletop, it's kind of manageable to entangle them. It's hard, definitely, but it's manageable. That's what we saw in the previous part. But what if they are far away? The quantum machines that people not usually, but nowadays the best quantum machines that people have are superconducting qubits. And if you want to connect them with microwave connectors at different labs, you would run into serious problem because they would be super lossy and noisy. So it would be good if we could communicate with optical frequencies at long distances, because in that case, the loss would be manageable, but at the expense of needing to do transduction. So the plan on our side is to send an entangled source in optical domain, which is prone to loss. There is no, even for really large amounts of loss, some entanglement would survive in two-mode squeezed vacuum states, which are basically entangled versions of, which basically are entangled two-photon states. And then each party needs to down convert it to microwave to be able to use that for the quantum machines that they have already at their lab. So this is just as, I will not spend that much time on this plot. This is just a reminder of what NOPA does, what I had in that last slide. And NOPA is a device that basically spits out a signal and idler which are entangled. And if your incoming fields to your NOPA are broadbanded, then you can show that your signal and idler out of the NOPA have correlations among negative opposite sidebands. So this is a schematic of the transducer that we are planning to use or characterize, understand more, at least in the theory part of the collaboration. And you can look at this paper out of Konrad Leonard's group. And as you see, there is a mechanical resonator here, which modifies both the resonance frequency of this Fabry Pro cavity as well as the resonance frequency of this LC circuit. And that's how this device connects the excitations between the microwave and optical. Notice the difference between the frequencies that we are working on here, gigahertz and hundreds of terahertz. So that's where the magic happens actually. And again, let me look at the diagram of the transducer. And the simplest form, again, you would have three harmonic oscillators, which each one of them are in contact with their own environment, let's say, with different coupling rates. And again, I'm going to employ input-output relationships or input-output formalism to study this system. Remember, input-output was about including Hamiltonian part as well as the non-unitary evolution of the system. So the Hamiltonian of the transducer is something like this. That is how the mechanics couples to the optical, and this is how the mechanics couples to the electrical part. This is basically because of radiation pressure. And here I'm in the rotating frame of the pumps. You do get the linearized Hamiltonian by a sequence of approximations. And what I do here is linearize the Hamiltonian, definitely. Obviously, it means that you replace the fields with their strong classical magnitude plus some quantum fluctuations. This is an approximation which is well met in the nowadays experiments. And if you go in the red sideband regime, which is a technical term which I do not care, we do not care about it at the moment, and throw out some terms which are linear, at the dynamics that we care about, you will end up with this simplified Hamiltonian. And again, as before, you would end up with these Heisenberg-Langevin equations of motion. Just as a reminder, if the system was closed, this would be your Heisenberg equations of motions. But now that you have couplings or talks to the environment for each one of these oscillators, under certain assumptions that are met in the experiment, you can slightly modify these equations of motions for the fields of optical, microwave, and mechanical fields. What are the relevant statistics if I want to study this problem? The incoming fields and the optical part. Remember, you have two transducers. You are sharing an entanglement source in optical, and then each one of the labs have to transduce it or down convert it to microwave. The incoming fields out of a NOPA, which is your entangled resource in optical domain. Definitely, there is some correlation between those two. That's what it means to share an entangled resource between those two at far distances. But then whenever you want to read the fields inside the cavities in each of those labs in the microwave domain, again, like that police car example, you shine a laser and then you read off the reflected field. The field that you use as the probe or your input field is definitely uncorrelated. They are using different fields in their own labs, but we hope to see some entanglement in the output fields because we hope to see some entanglement between the fields inside the cavities. So this is just this may not be that much. This is not an elegant plot, I would say, but this is just to show that when I do simulate this system on my computer, you would see some correlation between opposite sidebands of the microwave fields. What are we seeing here? This is the magnitude of the outgoing field or reflected microwave fields in two remote labs, and zero frequency is the central frequency of the pumps. The fact that you are using some broad-banded fields means that you would have frequency offsets, and the fact that the two states are entangled, you would see there is some correlation between the opposite sidebands. So this is what we expected from the beginning, and that's what we see actually in the numerics so far. And this is just a plot to show that if you manage to realize large optomechanical and electromechanical coupling rates, you definitely, at least in this approximation, you can end up with entanglement in the outgoing fields on the microwave ends to different locations. But according to my experimental colleagues, coming up with this amount of rates is a challenge. So this is definitely an ongoing study. So just to summarize, on the first part, I presented our results regarding the establishment of entanglement between two macroscopic mechanical objects. And in the second part, I formulated the process of transduction and studied the feasibility of entangling two remote microwave fields by sharing an optical two-mode entangled state. And with that, thank you. That's
all right. Thank you, Ezad. We still, our next speaker starts in 3 minutes. We could maybe do like a one very quick question if anyone had anything they wanted to ask of Ezad before we move on.
I had a question. In the first part, you used the smallest eigenvalue of the covariance matrix as a measure for entanglement. Why did you choose this measure, and how does it relate to other measures of entanglement?
Yeah, just make sure it's the smallest minimum symplectic eigenvalue that's different from the covariance matrix's eigenvalue. But the thing that is to keep that in mind is that's basically the Perez-Hordicki criteria. So Perez-Hordicki criteria for entanglement, you can show that is equivalent to the measure that we used in this experiment. So whenever you have CV quantum systems, it kind of makes sense to gain anything you want by just looking at the covariance matrix, right? Because whatever information you need is there. And I need to emphasize that there's not something special or magical about this minimum symplectic eigenvalue. This measure is equivalent to Perez-Hordicki, which is the measure. Perez-Hordicki is not if and only if, but as Mike corrected me there, if you have partial transpose to be, if your state is separable, then partial transpose is positive. The equivalent, our measure is basically that in CV quantum, in CV Gaussian state domain.
Just to follow on to that, Victor, the theory of entanglement for two-mode bosonic Gaussian states is much simpler. And so you just work through a sequence of steps and then you arrive at the conclusion Ezad was talking about.
So is this measure like the same measure that you would get out of, say, majorization?
I think it's related to the negativity.
Yeah, that's basically related to log of negativity. Yeah.
Yeah.
All right. So let's move on. It's 1:50.